So this video is on limiting reagents and excess reagents. Now, unless the reactants are put in perfect stoichiometric proportions, one of the reactants, if the reaction goes to completion, is going to be completely consumed. We're going to call that the limiter, or the limiting reagent. It's a reactant. Okay? And this is going to be consumed completely. And the other reactant or reactants, there could be three, there could be more than two, is going to be called the excess. And there's going to be some of that left over. Essentially what that means is if for every one molecule you don't have exactly 3 molecules of hydrogen in your reaction vessel, then one or the other one is going to have some stuff left over. It's sort of like, if you're using 5 ingredients to make a recipe, well, you might run out of one ingredient, but you're not going to run out of all 5. You'll have something left over and have to use it for a different recipe. Okay, so we can do this problem by inspection. Okay, by simply doing this, we can go, okay, 1 molecule of nitrogen, 1, 2, 3 molecules of hydrogen. 1 molecule of nitrogen, 1, 2, 3 molecules of hydrogen. 1 molecule of nitrogen, 1, 2, 3. One more molecule, 1, 2, 3. And what you can see here is we have some nitrogen left over. And the reason why I did 1 to 3 is because for every 1 molecule of nitrogen, I'm going to consume 3 molecules of hydrogen to make 2 molecules of ammonia. So we can imagine what we're going to have in our reaction vessel when we've reached what's called completion. And by the way, this particular reaction would not go to completion unless we were removing product as it was made. We'll talk more about that later when we get to equilibrium. So what would be in the reaction vessel at the end? Well, this is your classic limiting reagent problem. You know what your limiter is because you basically ran out of hydrogen. So you now know there's going to be no hydrogen in the reaction vessel. You know your limiting reagent is this stuff, the hydrogen, the H2. You know that your excess reagent, okay, is this stuff, the nitrogen, because there's 3 molecules, and you can think of that as moles left over, right? So in your final reaction vessel, you're going to have 3 molecules of nitrogen floating around that never did any reaction because there was no hydrogen. Oh, I'm sorry, not 3. Ooh, bad math. 5 molecules. Okay, so I'll put 2 more in there. I have 5 molecules of nitrogen remaining that are unreacted, and I can put in my molecules of ammonia as well. Now, since I can see that I used up 1, okay, I'll X them so they're clear, 2, 3, 4 molecules of nitrogen, I can figure out how many molecules of ammonia I'm going to have in my final reaction vessel just by looking at that. If I have 4 molecules of nitrogen completely consumed, or moles of nitrogen, I know how many moles of ammonia I made. And this is why moles are so easy. For every 1 mole of nitrogen, I get 2 moles of ammonia, so I'm going to have 8 moles of ammonia. So I'll draw 8 molecules of ammonia, each representing 1 mole. 1, 2, 3. And this illustrates the basic idea. In a limiting reagent problem, they're going to ask you, okay, which is the limiter? How much of the excess reagent is left over, that's the nitrogen, and how much of the product we're going to make? Now, it's not always, first of all, they're not going to give it to you in moles. Secondly, it doesn't always work out like perfectly where one reactant gets completely consumed. Well, actually, let's just stop and look at a slightly different problem, which you can also do by inspection. The second part of this video will illustrate the math needed to determine the following: the limiting reagent, the excess reagent, the amount of excess reagent unreacted, and the amount of product that will be made, assuming the reaction goes to completion. In this example, we are starting off with 1, 2, 3, 4. That's 4 moles of nitrogen. We're going to say each molecule represents 6 times 10 to the 23rd molecules. And we have 10 moles of hydrogen. Now, this first step is the most critical one. There's lots of ways of determining what the limiter or the excess is. You can ask me later about other methods which are equally valid, and I'll say they're equally valid, but I'm going to do it one way for now to avoid confusion. So what I would do is I would go for every, make up a little factor label thing here, and I would go for every 1 mole of N2, 3 moles of hydrogen would have to be consumed. And I do the same thing down here. I go for every 3 moles of hydrogen, 1 mole of N2 is going to be consumed. And then I would just do the math here for both of them. and then I will analyze this. So 12 moles of hydrogen, because 3 times 4 is 12, and 10 divided by 3 is going to give me 3.33 moles of nitrogen. All right, so what does this tell me? This tells me that if all 4 moles of nitrogen were to react, I would need to have 12 moles of hydrogen. I don't have 12 moles of hydrogen. So all of the nitrogen will not be able to react. That's the key idea. Since there's not enough hydrogen around, we know that this is the excess reagent. And we also know that this is going to be the limiter. And that means all the hydrogen is going to react, which means we now know that exactly 10 moles of hydrogen will react. And the limiter is going to determine how much of the other reactant will be consumed, the excess one. So here's the important things we know. We know exactly how much hydrogen is going to be consumed, because for every 10 moles of hydrogen, we consume 3.33 moles of nitrogen, meaning there's going to be some nitrogen left over, but no hydrogen. So how much nitrogen is left over? Well, here's the deal. We know this is excess. We know hydrogen is the limiter now, right? How much nitrogen is left over? Well, we start with 4 moles of nitrogen. If 3.33 moles of nitrogen are consumed, we're going to have some excess left over, which is what we expect, 0.67 mole of N2. That this is the critical step, because at this point we know the important things. We know exactly how much nitrogen is going to be consumed, exactly how much hydrogen is going to be consumed. Once we're done with that, we can figure out how much ammonia will be made. And we can do that with either of the numbers I've just circled. Because what? If 10 moles of hydrogen are consumed, or 3.33 moles of nitrogen are consumed in the process, the stoichiometry shows that both of them will lead us to making the exact same amount of ammonia. Why? Because these two numbers here are in perfect stoichiometric proportions. They're in a 3-to-1 ratio, just like the equation. So so what I'm going to do here is for every 3 moles of hydrogen, I get 2 moles of ammonia, which is going to be equal to 6.66 moles of ammonia. All right, because 2/3 of 10 is 6.66. And for every 1 mole of nitrogen, I get 2 moles of ammonia, which is also equal to 6.66 moles of ammonia. In summary, if you're given things in grams or other units other than liters, which we'll talk about later, convert the stuff to moles. So the first step is always going to be convert to moles. 2, determine what the excess or limiter is. Once you know the quantities consumed, you can then use that consumed quantity to figure out how much product is being made. And you should know the quantities of both reactants being consumed by the end of the introductory part of the process.